Hello friends, we have studied the exact solution of Navier-Stokes equation. Now we have to apply that exact solution in real life condition. So one of the real life conditions which we have that is a fluid which is flowing in a horizontal direction. So we have to apply the exact solution of Navier-Stokes equation on this real life flow. So let us see, this is a real life situation where the flow is called as a Couette flow. Pardon my spelling for Couette. Anyways, so let us solve this part. So in which we have first initially got u as a function of y, which was solution of Navier-Stokes equation. So u is equals to that is plus 1 upon 2 mu dp by dx into y square plus y times c1 plus c2. So now, what is a Couette flow? Couette flow is a flow in which you have a horizontal surface and the fluid is flowing over this horizontal first surface, and there is an object which is kept on the top surface of the fluid. So we know that over here the fluid velocity at y is equals to 0, u will be equals to 0, because this is the initial layer which has maximum viscosity, and we consider this as no slip condition in which the fluid does not slip over the solid surface. We consider this as no slip condition, due to which it does not slip over the solid surface and the velocity is 0. As it goes away from this part, it will go from minimum velocity to maximum velocity. So at y is equals to h, this vertical height is h, the topmost velocity is equals to capital U. Let us consider this as capital U. So we have this differential equation. We have defined the boundary condition for a simple Couette flow. We have to just substitute the boundary condition in the solution of the differential equation. So now let us substitute this. The first boundary condition, which is y is equals to 0, u is equals to 0, where u is equals to 1 upon 2 mu dp by dx into y square plus y into c1 plus c2. So if you substitute this boundary condition, what do we get? The value of c2 is equals to 0. This part is 0, this part is 0, and this part is 0. All the three terms containing y and u are 0. So then your differential equation becomes, that is u is equals to 1 upon 2 mu dp by dx into y square plus y times c1. Then let us apply the second boundary condition, that is when y is equals to h, u will be equals to u max. So this is the part where u is equals to u max or maximum velocity. So instead of y, we have to substitute the value of h. So capital U will be equals to 1 upon 2 mu dp by dx, and instead of y square, we should substitute h square plus h times into c1. So let us calculate the value of C1. So C1 will be given as, this is U minus 1 upon 2 mu dou P by dou X into H square is equals to H times C1. So this will be given as U upon H 1 minus 1 upon 2 mu dou P, rather dP by dx into H is equals to C1. So we have got value of C1. So now our previous equation was U is equals to 1 upon 2 mu dP, not dou P, dP by dx into y square plus value of C1 we have to substitute. So this is y into u upon h minus 1 upon 2 mu dp by dx into h. Now let us evaluate this part. So what do we get over here? That is u is equal, so let us take this common, that is dp by dx 1 upon 2 mu. From these two terms we'll take this as common, so this is 1 upon 2 mu dp by dx into what we have over here is y square minus h, this is from this term, plus we have over here y into u upon h, so this is the second term. So this is actually what is the solution of this equation for a Couette flow. Now if we consider a simple Couette flow, over here, for simple Couette flow dp by dx is equals to 0. We do not consider the effect of pressure gradient, so that time you will get this as u equals to, that is u is equals to, this part will be 0 over here, this part dp by dx is equals to 0, this entire term will be 0, so that u will be equals to, small u will be equals to y times capital U upon h. So now we know that the value of h is going to remain constant, that is the height of that entire fluid above the solid surface, and maximum velocity at the top surface is also going to remain constant. So you get y as a function, we get u as a function of y, and the relationship is linear. So that means what, how this is going to change in the fluid flow. So over here y is equals to 0 at the bottommost surface, u is equals to 0, y is equals to h, u will be equals to capital H. During this part, the relation for a simple Couette flow is going to be a linear term, and over here the velocity is linearly increasing. So this is how it will increase. But for a just a Couette flow, here also y is equals to 0, u is equals to 0, and y is equals to h, u will be equals to, now this is capital U and this is capital U. This will be somewhat like this, because over here, because in this part we can see that it is a function of y square, hence it is going to roll out like this. So it is going to increase in a quadratic curve, and this is a linear curve. So this is a Couette flow, and this is a simple Couette flow. I hope you have understood how to derive a Couette flow and a simple Couette flow, considering the boundary condition and substituting the boundary condition in the solution of Navier-Stokes equation. Thank you.